Hello, this is Jake Abbott. In this video, we're going to be talking about the Kalman filter. In continuous time, we'll talk about the discrete time Kalman filter in the next video. The Kalman filter is really a topic from an optimal controls class and optimal controls text, but it's so common and it's easy to use even if you don't see its full development, if you know how to use it properly. So this is really just an introduction to the Kalman filter. If you're curious about more information, you're going to have to seek other sources. It's analogous to the LQR controller, which we've seen previously. The LQR controller we found was a way that it was the linear quadratic regulator. It was a way to choose our controller gains that went beyond just simply placing the eigenvalues of our system somewhere. It tied the choice of the controller gains more closely to the actual system performance. The Kalman filter is an analogy to the LQR controller. The LQR controller was about choosing optimal controller gains. What the Kalman gain is, the Kalman filter is about choosing optimal observer gains. And we're going to do that using knowledge of the kind of noise that our system's going to have on it. So let's recall the linear system that we're talking about. Looks like x dot is equal to ax plus bu, and y is equal to, and in general these are vectors, c times x. So what the Kalman filter does is it acknowledges that this model is not really correct. Even if you assume your system is linear, it's unrealistic to think that your system will have no other inputs besides the actuators that you have control over. And in general, there's some disturbance vector, d, that is going to push your states around. So if you look at the way that d interacts here, d directly affects your x dot. So these disturbances, they push your states in one way or another. And so if you think about the dimensions of this too, this is an n by 1 vector, just like your state vector is an n by 1 vector. And we're going to have these sensors y, but in actuality, our sensors aren't a pure representation of our states through this matrix C, but those sensors are going to be noisy things. And so we're going to have this noise vector n, and this is going to be the same dimensions as our output. So we've been calling this q. So this is a q by 1 vector. So in reality, this is the system that we have. And we'd like our system, if we make a nice control system, we'd like our system to sort of reject these things and say, on average, can I sort of not have noise affect me super badly, and can I not have disturbance D affect me super badly? It would be unrealistic to think that they won't affect you at all, because they're there and you don't really know them very well, so it's unrealistic to think you could completely reject them. But our goal is to try and reject them as well as possible. So we've designed a closed loop observer. I mean, we started with designing an open loop observer for X. That's this simulation of our plant that we run in parallel to our actual system, and we do this in order to estimate the states for full state feedback. We said we can implement an open loop observer, but it's not really great because we're stuck with the stability and time domain properties of our original system, and we'd like to have our stability properties be always stable, and we'd like our time domain properties to be probably much faster than the plant we're trying to control. So we said we're going to implement a closed loop observer, where we have this observer gain L, and we take the difference between our sensors and our excuse me, this should be a hat. So we take the difference between our sensors, our actual sensors that are coming out, and our observer sensors, and we use that difference to push our system around. And we said if we do this, then we're going to get a closed loop observer that has the closed loop characteristic equation that has this A minus LC. So these are the eigenvalues of our closed loop observer system, and we can place those wherever we want. So we've covered this before. And so what we want to do now is we want to define this error between our actual state and our observer state. I'm going to define it by this delta x, and that's going to be x minus x hat. So ideally what we want is we want this error to be 0, or as close to 0 as we can. We want our observer to perfectly give us our states. I'm just going to define this error in y the same way, so that it is just equal to c times delta x. So it's basically this same term here. So it turns out if you go through the math and you plug in all of these things into one closed loop system, and you write an equation for the dynamics of this error in state. So remember, this variable delta x is the error in our states, and we can watch that error evolve in time just like any other signal. If you go through and write the dynamics of this system out, you get a minus LC times delta x plus the disturbance minus the observer gain times the noise. So, we've already designed this A minus LC to be a nice stable system with dynamic properties that we want. And so you can imagine if, let's say for a minute we don't give any disturbance or noise, and we start with some initial error between our estimate of our states and our actual states. Well, that error is going to decay away to 0 with known time constants, and that was the original result of the closed loop observer. But we see that if ever a disturbance comes in into our states, or a noise comes into our sensors, that effectively acts like an input to this system. So that's going to disturb this error away from 0. And so anytime one of these disturbances or noises comes in, we're going to get a new error in our states, and as long as that disturbance goes away, then that error again is going to decay away to 0. But if these disturbances and noises keep coming, they keep pushing our error away from 0, and then that error keeps trying to get itself back to 0 through this natural response. So the nice thing about this is this system is going to have these nice bounded input, bounded output properties. So as long as the disturbance is a bounded thing, it doesn't have to ever go to 0. It can just bounce around. But as long as it's bounded, and as long as the noise is bounded, then the error in your states is also going to be bounded. So we're always going to never have our observer be perfect, but it's going to stay within some sort of window. And the idea is we want that window to be kind of as small as possible, so that our observer is always giving us good estimates. So if we look at the Laplace transform of our output estimation error, we can start to get some insight into what we want these disturbances to look like. So I'm going to do the Laplace transform of delta y. And in general, it looks something like this. It looks like the identity matrix plus C Si minus A inverse L. And this is a big matrix, and that's inverted, times C times Si minus A inverse. And this is times our disturbance now in Laplace transform. So this whole thing here is the Laplace transform that goes in front of disturbance. So it's the Laplace transform from disturbances to errors in our output y. And then we have this other term, identity plus C Si minus A inverse L inverse C Si minus A inverse L. This is the only difference, times our noise. So we have these two big transfer matrices that relate noise and disturbance to our output y. It's hard to really make too much sense of what's going on here because of the matrix formulation, but if we just briefly consider a single output system, so that our y is just a scalar now, it can be easier to see what is exactly going on here. So now we're only looking at a single output system. So all of a sudden some of these matrix inverses become scalars. So if you think about the dimension of this parameter here, C is now a 1 by n thing, and L is an n by 1 thing. So we have the ability, this becomes a scalar, and so an inverse just means a divide by. So we can write things like that, and so I get this fraction here that looks like a 1 plus C Si minus A inverse L, and then in the numerator I have C Si minus A inverse. So this is the transfer function for disturbance, and then on this side I get the exact same denominator. And you get these same denominators because your characteristic equation of your system is always invariant to the types of signals that you pass through it. So, whether your system is fundamentally stable or unstable, that doesn't matter which signals you look at. You always get this same characteristic equation, the denominator. So now we have SI minus A inverse L. So this is the transfer function from noise. Okay, so now we can see if we limit ourselves to a single output system, we can see really clearly that the way the observer gains L come into play in the transfer functions from the disturbances on the states and the noise on the sensors. When you start looking at this, you start saying, what would we like? I mean, ideally, we don't want the disturbance or the noise to affect Y. We would like it if our Y was perfect and this delta Y was always a 0, regardless of D and N. So we'd really like both of these to be 0, ideally. So when you start looking at this one, we conclude we want L to be as big as possible. So I'm going to say we want L to go to infinity to reduce effects of D. Because if L goes to infinity, then this denominator becomes a 1 plus infinity, so it basically becomes infinity. And so we have anything divided by infinity is 0. So we want L to be really big. When we look at this transfer function, we see we want L to be as small as possible to reduce the effects of noise. So imagine what happens as L goes to 0. On the denominator you have 1 plus 0, which is 1, and in the numerator you have a 0, so 0 over 1 is 0. So basically we have these competing effects, which isn't great for us. It means there's no easy solution here. If they agreed with each other, then we would just choose L either really big or really small, and that would make sort of the perfect observer. The conclusion here is if L is small, we don't amplify the noise of our sensors, but this will only work if our model is very good and we have very low disturbances. Because, as an aside, the disturbances could be literal disturbances pushing on your states, or they could also be sort of errors in your model. Those appear as disturbances. So that's what happens if L is small, but if L is big, we find here that we can reject disturbances, including modeling errors, but our sensor noise then appears in our states. So we have these state estimates that look something like, if here's time and here's my estimate of one of my states, I get something rather than looking like this and rejecting it. It may reject disturbances very well, but this is what I actually get out, and that's what I'm passing through to my state feedback. And so if you pass that through to your state feedback, you'll also see that in your output. So your system, while it rejects disturbances very well, will sit and jitter around its target value. You can make your L gain smaller to reduce the effects of that, so your output doesn't sit and jitter, but then it doesn't reject disturbances as well, and it doesn't reject modeling errors as well. So there's no sort of simple solution. There's no perfect solution. So our goal is to find a reasonable trade-off to balance these two effects. And that's exactly what the Kalman filter does. So when you hear the term Kalman filter, all a Kalman filter is a choice for the gains in L. A Kalman filter is our perfect observer gains, and it's going to be perfect assuming stochastic models of our disturbance and our noise and our initial estimation of our initial state. So that's what a Kalman filter is. It's the optimal choice of these gains L, just like a LQR controller was the optimal choice for the gains K under certain assumptions about our system. So for this development of the Kalman filter, we're going to make some assumptions about the stochastic properties of our disturbance and our noise. So remember, if we have this thing d of t, disturbance of t, it's an n by 1 vector. So it's got something like this, there's something like this. And each one of these signals, so if I look at d1 of t, they're signals that are evolving in time, each one of these things. And you could imagine them, kind of just doing something like this and bouncing around. And so in the Kalman filter development, there are some assumptions that are made on the properties of these signals. Okay? And there are a few of these properties. One is that, so this is going to apply to both d of t and n of t. So both the disturbance and the noise. First, it's going to assume they're stationary. That just means they're not evolving in time. So at any given instant in time, the stochastic properties are the same as any other instant in time. They're zero, mean, and Gaussian. And what that means is if I take the zero, mean, and Gaussian means I get sort of the standard bell curve that has all of the, properties of a bell curve, and zero mean means it's centered around zero. So on average, the disturbance or the noise is going to be zero, and it'll be a little above zero, and it'll be a little below zero. And the farther away you go from zero, the less likely it is to happen. And if you want to see, you can figure out the area under the curve between any two regions, and the area under that curve will be the probability that at any given instant it will be between those two regions. And the area under the entire curve is 1, so there's a 100% probability it will be somewhere under the curve. And then finally, the last thing that we use to describe this noise is we say it's white noise. And so white noise basically means if at one sample I measure my disturbance and it's right here, at the next instant in time, even if it's a millionth of a second later, it's equally likely, the disturbance is equally likely to be anywhere else on the distribution. It's not more likely to happen just because my disturbance is here. At the next instant in time, it's not more likely that it's going to be here because it's close or something. So it can jump around. The disturbance can be here, and a millionth of a second later it can be here, and another millionth of a second later it can be here. So it completely bounces around. But it always has, on average, it has a mean at 0, and then it has some sort of variance or standard deviation that describes sort of the likelihood that it will be between any two bounds. So we're going to make this assumption about all of our noises, and it would be reasonable for a reasonable person to say, I don't know if my disturbances and my noises are like this. And so often what people do is they take noises and disturbances that they know for a fact are not zero mean stationary Gaussian white noise processes, and they model them that way anyway, because it turns out that the Kalman filter is fairly robust to these things. So if you can sort of approximate a mean and a rough variance of your noise, and then use these Kalman filters and to choose your observer gains, the system it gives you will be really well performed, and it might not be completely optimal, but it'll be very close to optimal, and it'll still be a good approximately optimal system for you. So this sort of notion is built into all of our noises, and then the last thing it does is we have to talk about the variance. So basically, we know this thing is centered around 0 for each of these, but how is it spread out? So, if this is sort of 1 standard deviation and this is 2 standard deviations, how do we describe that size of that? And so what we do is we say the expected value of the term d of t, which remember is an n by 1 vector, times d of t transpose. So now this thing at n by 1 times a 1 by n is an n by n thing. So this is a big n by n matrix. So the expected value of, this is a t and this is a tau. So these are not taken at the same instant in time. This thing is going to equal some big matrix, which is an n by n matrix, times v, times the Dirac delta function evaluated at t minus tau. And let's, as an aside, talk about what that Dirac delta function is again. We've seen this before in this class. So remember that the Dirac delta function is this function, t minus tau. It's this function that's equal to 1 if t is equal to tau. So basically, when the thing inside the parentheses is 0, this is a 1. And it's a 0 if t is not equal to tau. So the Dirac delta function was this thing that we march along here at 0, 0, 0, 0, and then it spikes or excuse me, I shouldn't say Dirac delta, I should say Kronecker delta. It comes over like this, it spikes at 1, and then it's 0 again. So the Dirac delta function, if we start looking at this, what we're saying is, this is again a product of this being white noise. So if I take a disturbance at any instant in time, and this is a whole disturbance vector, and I multiply it with another disturbance vector at any other instant in time, if those two instants in time aren't the same, then the expected value, which is the average value, is going to be 0. So this thing's going to be 0 if they're not the same time. And if they are the same time, so if I take disturbance right now and I basically times it by itself, V is the thing that's capturing the approximate size of this. So it's essentially capturing the variance. So V is capturing the size of D with the assumption that they're at any different times they have really nothing to do with each other. So this is just a 0. And then we do the same thing for the noises. So we say the expected value of our noise, n at sample t times n at time tau transpose, and so this is a big q by q matrix, is equal to W times the Dirac, or I keep saying Dirac, but it's the Kronecker delta. So this is a big q by q matrix that looks very similar to this. So these matrices V and W basically encapsulate the size of our disturbance and the size of our noise. And when I say size, it's more in this kind of variance way, right? So you can think of, if this is the process for any one of our disturbances or noise, you can think of the value in V or the value in W essentially being kind of this value here. So how big is the spread of this thing? To get a little bit better sense of expected value just means average value. So let's think of something we have good intuition for. So what's the expected value of a roll of the dice? So if I roll a dice, it can either be a 1 or a 2 or a 3 or a 4 or a 5 or a 6. So those are the values that it can possibly take. And at any given roll of the dice, you don't know what value it will take. It will definitely take one of these 6. And there are 6 different choices, so I can average over 6. And if I do that, I'll get the number 3.5. So we would call the expected value of a dice roll equal to 3.5. So, it basically, a 3.5 roughly captures, on average, if I roll a dice, how big is the number that's going to come up. And on average, it comes up at 3.5. And if you do that enough times, you'll see that's the case. So the expected value is this way to encapsulate the average value that a random thing will come up. Okay, so we've said that this disturbance value on average is captured by V, the matrix V. We've seen that the noise value on average is captured by the matrix W. We have to say that V and W are both positive definite matrices, and that's just going to come out of the fact that you're taking numbers and timesing by themselves. So every element is in V is essentially a disturbance value times itself. So whether that disturbance value is positive or negative doesn't matter, because when you square it, it's positive. So these are going to come out to be positive definite matrices. And remember, just a quick review of what a positive definite matrix is. A positive definite matrix, if you take any vector x, left multiply it with this x transpose, and right multiply it like this, a positive definite matrix will always give you, that will always be a positive number for any possible x you can imagine. So V and W are positive definite matrices, and in general, I guess it's true that they're just positive definite with, they actually could be 0, but we are going to assume that W is actually strictly positive definite, meaning that there are no clean sensors at all. Every single sensor has some noise on it, so it's impossible for you to ever get any zeros in this matrix. So we've now characterized our disturbances and our sensor noise, but we also are going to have to start our system with some estimate of our initial state, and that's going to have some error associated with it too. So let's say our initial state is going to have some mean and covariance that's very similar. So let's say initial state x naught is going to have an expected value. This is the definition of this thing, is the expected value of our initial state, so our state at time 0. So, and then we're going to say that we're going to call this big matrix sigma naught. We're going to say that's the expected value of, I'm going to take my x at time 0, and then I'm going to subtract this expected value off. And that's a vector, that's an n by 1 vector. And then I'm going to take that and I'm going to times it by the same thing. Okay, so let's think about what we're saying here. We're basically saying we don't know our initial state, but we have some idea about how far off we might be, right? So we know on average our initial state is somewhere between some bounds or something, right? So on average our initial state is something around here, and that's what we call x naught. So that's sort of that's our best guess of our initial state. And then this next term, this big matrix down here, encapsulates basically how far off we might be from that best guess of our initial state. So we have these properties that describe our initial state, and then the last thing we want to say about the stochastic nature of our system is we want to assume that our disturbance d, our noise n, and our initial state x are all mutually uncorrelated. So basically, this goes back to this idea that these processes are these Gaussian white noise processes that the measurement at any one time has no effect on the measurement at any other time. And we say they're mutually uncorrelated, we're saying that they don't affect each other. So when the disturbance is high, that doesn't mean the sensor noise is high. The disturbance could be high and the sensor noise could be low. The disturbance could be low and the sensor noise could be 0. There's no correlation between them. And the way that we write that is we say the expected value of our disturbance at some instant in time times our noise at some instant tau that's going to be different than time is going to be equal to 0. We say that the expected value of our initial state and our disturbance at some different time, we say this thing is going to be 0. And we say the expected value of our initial state and our noise evaluated at some other time tau, we say this is going to be equal to 0. And we hold this true for all t and for all tau. So basically, on average, the disturbance, noise, and initial state have absolutely nothing to do with each other, and on average, they're going to average themselves out to 0. Okay, so now we're done talking about the stochastic nature of our different signals that we're assuming, and now our goal in the Kalman filter is we want to choose our observer gains L to minimize the expected value in our error in our states. So if you look at this, the dimensions of this thing, this is this n by 1 thing, this is now a 1 by n thing, so this is a scalar. And so you can think of this scalar evolving in time, and remember delta x is the difference between our actual states and our observer states. So this term here is really basically encapsulating the error between your observer states and your observer states and your actual states, and it's a scalar. So this is a signal that's evolving in time, and it's going to do something like this. And what we want to do is we want to, oh, excuse me, I shouldn't have drawn this below 0 though. That's not correct actually. You know, if you think about this, it's being times by itself here, so you're always going to get a positive number coming out. So it's something that's going to look like this. And our goal here is to choose L such that this is as small as possible. So we're going to try and minimize the error between our observer and our actual states. So with all of that development, we're not going to go through the whole proof of how the Kalman filter comes about, but it's developed in a very similar way to the LQR controller, and this Riccati equation appears again. And so here's to sort of summarize the result of the Kalman filter. It says, first we assume that the pair AC is observable. That's fundamentally built into this, this method. So it also turns out that we need the pair AV. Remember, A is our system matrix, but V is this matrix that encapsulates the size of our disturbance. We say that this thing has to be stabilizable. And remember, stabilizable doesn't mean controllable. It means less than controllable, but it means that the things you don't have control over are already stable. So we say if we know that pair AC is observable and AV is stabilizable, then the optimal estimator gain, the gain that is the Kalman filter gain, will be found using L equals sigma, and let's call this sigma bar, times C transpose times W inverse. So C transpose is our C matrix transpose. W encapsulates the size of our sensor noise. And what is this sigma bar? Sigma bar is the unique positive semi-definite solution to the dual algebraic Riccati equation. So the dual algebraic Riccati equation. And the dual algebraic Riccati equation is this. It's 0 equals sigma times A transpose, I'll say sigma bar, times A transpose plus A sigma bar plus V minus sigma bar C transpose W inverse C sigma bar. And so this equation here, called the dual algebraic Riccati equation, there's going to be a unique solution for this sigma bar. And you solve that numerically, and MATLAB has tools to do that, such as the function ARE in MATLAB. So you numerically solve for this unique solution for this sigma bar matrix, and then you use that solution to compute the optimal gains L. And if you design your observer in this way, then you're going to say you have the optimal observer for that trade-off between the disturbances and noises that you know to have in your system. The final thing I'd like to say is that in the event there's a name for this method. So if you design your controller using the LQR method, which is the linear quadratic regulator, and you design your observer using Kalman filter. So you design your controller gains this way. So I'll just say K here, and the observer gains L here. If you do both of these things, there's a name for this, and they call it a linear quadratic Gaussian controller. So if someone says they're designing using the LQG method or linear quadratic Gaussian, that simply means design your controller using linear quadratic regulator and design your observer using Kalman filter.